40 light-years away, there is a solar system so incredibly compact that all 7 of its rocky planets would fit comfortably inside our own Mercury. The fourth world in that system is TRAPPIST-1e. It is roughly Earth-sized, and it orbits at the exact distance where the temperature of its dim star allows for the possibility of liquid water. Because it sits so close to its star, the planet is almost certainly tidally locked. One side cooks in permanent daylight, the other freezes in eternal night. But right in the middle, along a narrow terminator line of perpetual twilight, the conditions for liquid oceans actually work. Because of this exact alignment, we have spent nearly a decade looking at TRAPPIST-1e as humanity's single best candidate for studying a potentially habitable exoplanet using the technology we have right now. But there is a catch. The star anchoring this system is a red dwarf. They are the most abundant type of star in the universe, and they are exceptionally violent. They regularly produce massive superflares that dwarf anything our own sun throws at us. Because the habitable zone around a red dwarf is incredibly tight, any planet sitting inside it is constantly bathed in a high-energy flood of X-rays and extreme ultraviolet light. When that intense radiation hits an atmosphere, it ionizes the gas. It strips the electrons right off the molecules, allowing those particles to be picked up and swept entirely out into space by the star's own solar wind. According to the math, this relentless stellar violence should guarantee that a planet like TRAPPIST-1e is completely stripped of its air. If a star shouts at a planet for billions of years, the atmosphere leaves. In late 2023, the James Webb Space Telescope challenged those models. Across 4 orbits, it stared at TRAPPIST-1e, detecting a faint atmospheric signal. It did this using transmission spectroscopy. For less than an hour, the planet passes directly between us and its star. A tiny fraction of that starlight grazes the edge of the planet, and as it passes through whatever thin envelope of gas sits on the surface, the light is altered. This chart shows exactly how astronomers read that light. A nitrogen molecule absorbs a slightly different shade of infrared than a methane molecule. When mapped onto a line graph, those specific missing wavelengths leave exact chemical fingerprints, precise dips corresponding to specific gases. But the graph we pull from the telescope is almost never clean. Because the planet is so small and the star is so dim, those tiny chemical fingerprints are nearly impossible to read. They are entirely buried under the erratic static of stellar flares and the noise of the detector itself. The signal the telescope picked up was so deeply buried in this noise, astronomers did not get a clear, distinct picture of the sky. Instead, they got a statistical whisper, forcing them to rely on a process of elimination. By running the noisy data against thousands of simulated atmospheres, the team made their first major elimination. TRAPPIST-1e is not a bare, irradiated rock. Some form of atmosphere has actually survived. They also ruled out a suffocating carbon dioxide-dominated atmosphere. Whatever air wraps around TRAPPIST-1e, it does not look like the ancient conditions of Mars. Instead, the statistical models point to a thin, secondary atmosphere that built up well after the planet finished forming, one dominated by nitrogen, with a tentative trace of methane. The closest chemical analog we have to a sky like that sits right in our own solar system. It is Titan, Saturn's largest moon. Finding a colder, drier version of Titan around a violent red dwarf creates a physical paradox. A nitrogen-methane sky should be stripped away in the blink of a geological eye, implying that an unseen force, extreme volcanism, or a massive magnetic field is constantly replenishing what the star steals. Here is the scientific reality of the situation. 4 planetary transits are mathematically insufficient to confirm this atmosphere. The signal is faint, and the instruments are being pushed to their absolute limits. Astronomers operate with an extreme culture of restraint. They know the cost of a misread spectrum, so they will deliberately understate a finding until the data leaves no room for doubt. Progress here is measured in increments. It is a grueling, multi-year accumulation of marginal data, a quiet shift in probability where one atmospheric model gradually gains a slight statistical preference over the noise. To turn this statistical hint into an undeniable confirmation, the team is currently using the Webb telescope to record 15 additional planetary transits. The full set of results from that massive observational campaign will be published in 2026. That is the year this atmospheric whisper will either be confirmed as a reality or dismissed entirely as an illusion. Confirmation would prove that the most common stellar environments in the universe are not the dead zones the models predicted. It would mean the galaxy is likely crowded with worlds that held on to their air despite the stars that raised them. Humanity has built a machine sensitive enough to read the atmospheric chemistry of a world 400 trillion kilometers away. But to get the answer, we have to endure the hardest part of science. We have to sit in the silence and wait for the universe to speak.